Every day, thousands of tons of sunflower seeds are transformed into pure golden oil through a high-speed industrial process few people ever see. From crushing and pressing to refining and bottling, sunflower oil production requires powerful machinery and non-stop efficiency. In this documentary, we take you inside the factory to uncover the full journey of the world's most popular cooking oil. The production of sunflower oil in modern industrial facilities is a meticulously orchestrated process that transforms raw sunflower seeds into the clear, golden oil commonly used in cooking and food production. This journey begins with the careful selection and preparation of sunflower seeds, ensuring that only the highest quality seeds are processed to produce premium oil. Upon arrival at the processing plant, sunflower seeds are subjected to a rigorous cleaning regimen designed to remove a variety of impurities that may have been introduced during harvesting and transportation. This initial phase is critical, as foreign materials such as soil, stones, plant debris, and metal fragments can compromise the efficiency of the extraction process and the quality of the final product. The cleaning process typically involves several stages, each employing specialized equipment tailored to eliminate specific types of contaminants. The first line of defense in the cleaning operation is the magnetic separator. This device utilizes powerful magnets to attract and remove ferrous metal particles from the stream of sunflower seeds. Metal contaminants can originate from various sources, including harvesting equipment and transport containers, and their removal is essential to prevent damage to downstream processing machinery and to ensure product safety. The seeds pass over or through magnetic plates or drums, where metallic impurities are captured and separated from the bulk material. Following magnetic separation, the seeds proceed to vibrating sieves or screens. These machines consist of perforated plates or mesh screens that oscillate at high frequencies, effectively sorting the seeds based on size and shape. Larger impurities, such as sticks, leaves, and oversized debris, are unable to pass through the screen openings and are thus separated from the smaller, uniform sunflower seeds. The vibration intensity and screen aperture sizes are carefully calibrated to optimize the removal of unwanted materials while minimizing the loss of viable seeds. To address the presence of denser contaminants like stones and clumps of soil, the cleaned seeds are then routed through destoners. Destoners operate on the principle of density separation, utilizing airflow and vibration to differentiate between heavier impurities and the lighter sunflower seeds. As the mixture is fed onto an inclined vibrating deck, air is blown through the material from below. The heavier stones resist the upward airflow and migrate to the higher end of the deck, where they are discharged, while the lighter seeds are carried by the vibration to the lower end for collection. This process effectively ensures that only cleaned seeds advance to the next stage of processing. After the comprehensive cleaning process, the sunflower seeds are ready for dehulling, also known as shelling. Sunflower seeds are encased in hard outer shells or hulls that constitute a significant portion of the seed's total weight. These hulls are low in oil content and can impede the extraction process if not removed. Therefore, dehulling is a crucial step aimed at increasing the efficiency of oil extraction and improving the quality of the resulting oil. The dehulling process begins with the conditioning of the seeds to facilitate the separation of the hulls from the kernels. Conditioning typically involves adjusting the moisture content of the seeds through controlled heating or humidification. Properly conditioned seeds have hulls that are more brittle and easier to crack, enhancing the effectiveness of the dehulling equipment. Once conditioned, the seeds are fed into dehulling machines, which employ mechanical forces to crack the hulls. One common type of dehuller is the centrifugal sheller, which uses a rotating impeller to hurl the seeds against a hard surface, causing the hulls to fracture upon impact. Another method involves the use of roller mills, where seeds pass between counter-rotating rollers that exert compressive and shear forces, breaking the hulls without damaging the kernels. The choice of dehulling equipment depends on factors such as seed variety, desired throughput, and specific plant configurations. Following the cracking of the hulls, the mixture of kernels and shell fragments undergoes a separation process to isolate the oil-rich kernels. This separation is typically achieved through a combination of aspiration and screening techniques. Aspiration involves the use of air streams to lift and remove the lighter hull fragments from the heavier kernels. The mixture is fed into an aspirator, where a controlled airflow lifts the less dense hulls away from the denser kernels, effectively segregating the two components. Screening may also be employed, utilizing vibrating screens with specific mesh sizes to further refine the separation based on particle size and shape. The efficiency of the dehulling and separation processes is paramount, as incomplete removal of hulls can lead to increased fiber content in the oil, affecting its clarity and stability. Moreover, residual hulls in the meal byproduct can diminish its nutritional value and marketability as animal feed. Therefore, processors often implement multiple passes through dehulling and separation equipment to achieve optimal results, balancing the trade-offs between processing time, energy consumption, and product quality. With the sunflower kernels now isolated and free from their hulls, they are ready to undergo further processing to extract the valuable oil contained within. The next stages involve mechanical pressing and/or solvent extraction, each with its own set of procedures and equipment designed to maximize oil yield and quality. These processes will be explored in detail in the subsequent sections, delving into the intricacies of transforming cleaned and dehulled sunflower seeds into the refined oil that reaches consumers worldwide. Now it's time to go into the core phase of sunflower oil manufacturing, the oil extraction process. This is where the golden liquid locked inside the sunflower kernels is separated and collected. The extraction phase typically uses one of two methods, or more commonly, a combination of both, for optimal oil recovery: mechanical pressing and solvent extraction. Each method has its own benefits and limitations, and modern sunflower oil factories are designed to seamlessly integrate these systems into a continuous, high-efficiency process that minimizes waste and maximizes yield. The first step in oil extraction is mechanical pressing, often referred to as expelling. In this process, the dehulled and cleaned sunflower kernels are conveyed into a series of screw presses, also known as oil expellers. These heavy-duty machines consist of a cylindrical barrel housing a rotating helical screw shaft. As the kernels are fed into the expeller from one end, the screw shaft compresses them with increasing pressure as they travel along the barrel. The space between the screw and the barrel gradually narrows, intensifying the pressure and causing the oil to be forced out through small perforations or slits in the barrel wall. This process is incredibly robust and continuous, with some industrial presses capable of handling several tons of seed per hour. However, mechanical pressing alone can only extract about 85% to 90% of the total oil content from sunflower seeds. The remaining 10% to 15% stays trapped in the pressed cake, a solid, fibrous byproduct that still contains a considerable amount of valuable oil. To retrieve this remaining oil and improve overall efficiency, factories employ solvent extraction. Before the solvent extraction phase begins, the pressed cake from the mechanical expeller must be properly prepared. This involves breaking the compacted cake into smaller, uniform pieces using a cake breaker or flaking mill. The flakes are then conveyed to a conditioning unit where they are heated to a specific temperature, usually between 60 to 80 degrees Celsius. This heating not only helps to soften the cell structure of the material, but also enhances the effectiveness of the solvent by improving oil solubility and fluidity. Once conditioned, the sunflower cake is fed into a continuous extractor, typically a horizontal rotary extractor or a loop extractor. In this large stainless steel apparatus, the cake is soaked with a food-grade solvent, most commonly hexane, which has an exceptional ability to dissolve oils. The cake moves slowly through the extractor on a perforated conveyor belt or through a series of baskets, while the solvent is sprayed from above and recirculated from below. As the hexane seeps through the material, it dissolves the residual oil, forming a solution known as micellar. This micellar, containing both oil and solvent, is then pumped out of the extractor and sent to a series of distillation units where the solvent is evaporated and recovered, leaving behind the crude sunflower oil. The evaporation process is conducted under vacuum and controlled heating conditions to ensure complete solvent recovery without degrading the oil. Simultaneously, the now oil-depleted cake, referred to as spent meal, is conveyed to a dissolventizing toaster. This equipment uses steam and indirect heat to remove any residual hexane from the meal, making it safe for use as high-protein animal feed. Next, let's look at the processing of crude sunflower oil, which, at this stage, is a deep amber liquid that contains several impurities, including free fatty acids, phospholipids, pigments, waxes, and trace metals. Though technically oil, this unrefined product is not yet suitable for cooking or bottling. It must be purified and stabilized through a multi-step refining process, which includes degumming, neutralization, bleaching, dewaxing, and deodorization. The first of these refining steps is degumming. In this phase, the crude oil is mixed with a small amount of water or a weak acid, such as citric or phosphoric acid. This causes the naturally occurring phospholipids, also known as gums, to become hydrated and coagulate into a heavier phase that can be separated through centrifugation. The removal of these gums is crucial because they can contribute to off flavors, reduce shelf life, and interfere with further refining stages. The centrifuges used here operate at extremely high speeds, up to 5,000 revolutions per minute, creating centrifugal forces strong enough to separate even microscopic droplets and particles. Once degummed, the oil is subjected to neutralization, where it is treated with a caustic soda solution to remove free fatty acids. These acids can contribute to rancidity and reduce the oil's stability, so their removal is vital for producing a high-quality, shelf-stable product. The soda reacts with the free fatty acids to form soap stock, which is then separated from the oil via another round of centrifugation. The soap stock may be further processed into industrial byproducts such as lubricants or fatty acid distillates, ensuring minimal waste. Now it's time for the bleaching phase. Despite its name, this stage does not involve any chlorine or harsh chemicals. Instead, the oil is mixed with an adsorbent clay material, often activated bleaching earth or acid-activated bentonite, that binds with pigments, trace metals, and other unwanted compounds. The mixture is then heated under vacuum and passed through a filtration system where the spent clay is removed, leaving behind a visibly lighter oil. The objective of this step is not only to improve the color, but also to remove pro-oxidants and residual contaminants that could impact the oil's flavor or stability. But up next is one of the most temperature-sensitive and critical steps: dewaxing. Sunflower oil naturally contains waxes that, while harmless, can cause cloudiness or sedimentation when the oil is refrigerated or stored at low temperatures. To ensure crystal clear oil, particularly for use in transparent bottles, the dewaxing process is implemented. The oil is cooled gradually in a crystallization tank to allow waxes to solidify, and then pass through chilling filters or plate and frame filter presses. The solidified waxes are captured by the filter media and removed, leaving the oil with improved cold stability and clarity. Finally, the last refining step is deodorization. This process removes volatile compounds, including aldehydes and ketones, that can impart undesirable flavors and odors to the oil. Deodorization is carried out in a high vacuum, high temperature distillation column where the oil is subjected to steam distillation at temperatures between 180 to 240 degrees Celsius. The high temperature causes the volatile substances to evaporate, and the vacuum ensures they are swiftly removed from the system. Modern deodorization systems include structured packing and multiple stripping trays that allow for efficient steam-oil contact with minimal thermal degradation of the oil. The end product of this exhaustive refining sequence is a brilliant, light yellow, odorless oil with a neutral flavor and excellent oxidative stability, qualities that make it ideal for cooking, frying, baking, and use in processed foods. The refined sunflower oil is now ready for bottling or bulk packaging, depending on its intended application, whether destined for supermarket shelves or as an ingredient in snack foods, margarine, or ready-to-eat meals. The oil's journey from seed to bottle is far from over. Now it's time to explore the next critical phase in the industrial sunflower oil production process, the packaging and distribution stage. After undergoing extensive cleaning, pressing, solvent extraction, and refining, the sunflower oil is now fully processed, brilliant in clarity, neutral in flavor, and stable for both cooking and long-term storage. But before it can reach consumers or be used by food manufacturers, the oil must pass through highly automated and carefully controlled packaging systems. These systems are designed to maintain product integrity, optimize shelf life, and meet regulatory and commercial requirements for both retail and industrial distribution. Once the refined sunflower oil leaves the deodorizer, it is pumped into large stainless steel holding tanks. These tanks are equipped with inert gas blanketing systems, typically using nitrogen, to prevent oxidative degradation of the oil. Even trace amounts of oxygen can initiate rancidity, so maintaining a low oxygen environment in storage is critical. The tanks are also thermally insulated and often jacketed for temperature control, maintaining the oil at a stable range of around 25 to 30 degrees Celsius. This ensures that the oil remains fluid and clear, preventing cloudiness that could otherwise form during cooler storage conditions. From these storage tanks, the oil is directed via stainless steel pipelines to the packaging area. The transfer lines are equipped with positive displacement pumps and high sensitivity flow meters to ensure precise, consistent delivery volumes. Before entering the filling systems, the oil passes through final filtration units, often made up of multi-layer stainless steel mesh or polymer filter cartridges to capture any microscopic particulates that may have entered during tank storage. This guarantees that only the cleanest, crystal clear oil reaches the packaging stage. The packaging line is often separated into two main tracks. One for retail-sized bottles, typically ranging from 500 milliliters to 5 liters, and another for bulk containers, such as 20-liter jerry cans, 200-liter drums, or 1,000-liter intermediate bulk containers for industrial clients. The retail packaging line begins with empty bottles being loaded onto a conveyor, either manually or through robotic depalletizers. These bottles are usually made from food-grade PET and are blow molded on-site or sourced from specialized suppliers. Before filling, every bottle passes through a bottle rinser, where a jet of filtered, compressed air or ozonated water is sprayed inside to remove any dust or particles. This ensures microbiological and particulate cleanliness before the oil is introduced. The cleaned bottles are then transferred to multi-head volumetric or gravimetric filling machines. These high-speed machines, capable of filling up to several hundred bottles per minute, are calibrated to extreme accuracy, ensuring every bottle contains the precise labeled volume, no more, no less. The filled bottles are immediately capped by rotary capping machines, which place and tighten tamper-evident screw caps or snap-fit closures. Some systems integrate induction sealing, where a foil liner inside the cap is sealed to the bottle mouth using electromagnetic energy. This creates an airtight, tamper-proof barrier that preserves freshness and prevents leakage during transit. After capping, bottles pass through labelers that apply pressure-sensitive or shrink-sleeve labels. These labels are printed with brand information, nutritional facts, batch codes, and expiration dates using high-speed inkjet or laser coders, allowing for complete traceability of every unit. Following labeling, bottles proceed through automated inspection systems equipped with cameras and sensors that verify fill levels, cap integrity, label alignment, and code legibility. Any non-compliant bottles are automatically rejected via pneumatic arms into separate bins for rework. Approved bottles continue along the line to automated cartoning and case packing stations, where robotic arms place them into cardboard cartons, followed by case sealing with hot melt glue or tape. For bulk packaging, a separate line handles large volume containers. These containers are positioned under filling nozzles that are often suspended from load cells to ensure accurate weight-based filling. Bulk fillers must also incorporate anti-foaming and venting mechanisms to prevent air entrapment, especially at high flow rates. Once filled, containers are sealed with heavy-duty caps or tamper-evident seals and palletized for shipping. All packaging configurations, whether for retail or industrial use, are assigned unique identifiers linked to the master production batch and logged in the plant's ERP system. Now it's time to delve into the logistics and distribution chain, which plays an equally crucial role in maintaining the sunflower oil's quality and ensuring timely delivery to global markets. Once the packaged oil is palletized, it is moved via autonomous guided vehicles or forklifts to climate-controlled storage warehouses. These warehouses are designed for high throughput and efficient inventory turnover. Pallets are organized using barcoded location systems, and warehouse management software ensures that the oldest batches are shipped out first, following the FIFO principle. Transportation from the factory to distribution centers, wholesalers, retailers, or export terminals is typically conducted in temperature-regulated trucks or intermodal containers. For export shipments, ISO tank containers or food-grade flexi-tanks are used to transport sunflower oil in bulk volumes over long distances, often across continents. These tanks are insulated and equipped with inert gas blanketing systems to maintain oil stability during the journey. For local or regional deliveries, finished product pallets are shrink-wrapped, strapped, and loaded into trucks equipped with GPS tracking and real-time temperature monitoring. Each shipment includes digital delivery documents with QR codes or RFID tags that sync with customer inventory systems, facilitating seamless unloading and tracking upon arrival. Delivery confirmation, quality checks, and real-time feedback mechanisms are used to verify that every order arrives in optimal condition, both physically and chemically. But up next is one of the most critical dimensions of the modern sunflower oil industry: quality assurance and regulatory compliance. The food-grade nature of edible oil necessitates adherence to stringent quality standards at every stage of the process, from seed selection to final bottling. Every batch of sunflower oil is subjected to a comprehensive suite of analytical tests conducted in on-site laboratories or accredited third-party labs. These tests include parameters like free fatty acid levels, peroxide value, anisidine value, color, moisture content, and soap residue, all of which provide a comprehensive snapshot of oil quality and stability. Gas chromatography is used to profile fatty acid composition, ensuring the oil meets the standard range for linoleic and oleic acid contents. Spectrophotometers analyze color and clarity, while Carl Fisher titration determines residual moisture. These tests not only guarantee regulatory compliance with international standards like Codex Alimentarius, the European Union Food Safety Directives, and the US FDA guidelines, but also help refine internal production protocols. If any parameter falls outside the accepted range, the affected batch is isolated and either reprocessed or discarded. Up next, we focus on one of the more overlooked, yet incredibly vital components of sunflower oil production: byproduct utilization and factory process integration. Modern industrial sunflower oil facilities are designed not only to produce refined oil efficiently, but also to capitalize on every possible output from the sunflower seed itself. This means that even materials which, in earlier generations of oil production, may have been considered waste, are now valuable raw materials for secondary industries or reprocessed within the factory. One of the most important of these byproducts is the sunflower meal or cake that remains after the oil has been extracted. This dense, protein-rich substance is collected immediately following the dissolventizing process and cooled using air blast or counterflow cooling systems to bring the temperature down from over 100 degrees Celsius to ambient levels. This temperature drop is necessary to preserve protein quality and prevent mold growth during storage. The cooled meal is then ground into a uniform particle size using hammer mills or roller mills and passed through vibrating screens to remove any oversized clumps. Sunflower meal is widely used in the livestock and poultry industries as a valuable feed ingredient due to its high protein content and favorable amino acid profile. Factories that produce sunflower oil at scale often have integrated bagging or bulk loading systems for the meal, allowing it to be packaged into 25 or 50 kilogram bags or loaded into bulk silos for shipment in trucks and rail cars. Some facilities even have in-house pelletizing systems that compress the meal into pellets, which are easier to handle, store, and transport. Another byproduct generated during processing is the husk or hull removed during the dehulling stage. These hulls, although devoid of oil and low in protein, have significant value as a biomass fuel. Many sunflower oil factories have transitioned to using these hulls as a renewable energy source to generate heat or steam for use in the facility. The hulls are fed into biomass boilers equipped with particulate filters and emissions control systems where they are combusted cleanly and efficiently. The steam produced powers heat exchangers for oil refining processes like bleaching, deodorization, and dewaxing, reducing reliance on fossil fuels and lowering the factory's carbon footprint. In more advanced facilities, excess steam from the coal-fired boilers is also used to drive small steam turbines, generating on-site electricity that supports lighting, automation systems, and auxiliary equipment. This form of cogeneration enhances energy efficiency and contributes to the plant's sustainability targets. Some operations even sell surplus energy back to the local grid, turning what was once a waste product into a revenue stream. Water recycling is another critical area of integration. Given the extensive use of water in processes such as conditioning, steam generation, equipment washing, and degumming, a closed-loop water treatment system is essential. Wastewater from the plant is collected in large settling tanks, where solids are removed via sedimentation. The water then passes through biological treatment units and membrane filtration systems, such as reverse osmosis or ultrafiltration, to remove organic matter, oil residues, and chemical impurities. The treated water is reused in non-critical applications like boiler feed or equipment cleaning, drastically reducing freshwater consumption. Now turning to process automation, modern sunflower oil facilities operate as highly digitized environments where real-time data governs every aspect of production. Centralized control rooms equipped with HMI panels and SCADA systems provide operators with full visibility and control over temperature, pressure, flow rate, and other parameters at each processing step. Every sensor in the system, from tank-level monitors to flow meters and load cells, is networked to a control system that not only logs data for traceability, but also actively regulates inputs to maintain optimal efficiency. For example, if a temperature deviation is detected in a deodorization column, the SCADA system can automatically adjust the steam valve opening percentage to correct the temperature within seconds. Similarly, in the filling line, digital vision systems detect the fill level and reject any bottles that fall outside preset tolerances. This integration between mechanical systems and digital controls ensures the factory runs continuously with minimal human intervention, reducing errors and improving consistency. Predictive maintenance is another application of advanced automation in sunflower oil production. Vibration sensors, thermographic cameras, and acoustic monitors are placed on motors, gearboxes, pumps, and bearings to detect wear patterns long before failure occurs. The data is fed into AI-driven platforms that analyze trends and forecast the optimal time for maintenance. This prevents unplanned downtime, increases equipment lifespan, and maintains uninterrupted production flow. Inventory management and logistics are similarly digitized. Raw materials, finished oil, packaging supplies, and maintenance components are tracked using barcodes or RFID tags that interface with the plant's ERP system. This allows real-time monitoring of stock levels, automatic reordering when thresholds are reached, and optimized production scheduling based on available resources and demand forecasts. Finished goods are tracked through the entire supply chain, and shipping documents are generated automatically, reducing paperwork and human error. The industrial processing of honey begins not within the walls of the factory, but at the apiaries, where honeybees forage, collect nectar, and begin the complex enzymatic process of transforming floral sugars into the thick, golden liquid we know as honey. Factory-scale honey production starts with the careful coordination between contracted beekeepers and processing plants, which work together to supply bulk honey at a scale large enough to support mass distribution. The first step in the factory process involves the reception and inspection of raw honey as it arrives from the beekeepers' extraction sites. Raw honey is typically delivered in large food-grade steel drums or plastic totes, each capable of holding hundreds of pounds of honey. These containers arrive sealed, labeled with origin data, floral source if known, and batch tracking codes. Upon arrival at the honey processing facility, each container is unloaded onto the receiving dock, where a team of technicians begins the initial quality assurance process. This is far more than a visual check. Industrial honey processors must guarantee that the incoming product is pure, unadulterated, and meets strict legal and food safety standards. The drums are first sampled using a specialized honey sampling spear, a long stainless steel tube designed to pierce through the viscous mass and extract a vertical core from top to bottom. This is essential because honey can stratify, with moisture content, color, and crystallization levels varying from top to bottom. The extracted sample is then homogenized and sent to the quality control laboratory. Here, a battery of tests is performed. Moisture content is measured using refractometers, which determine how much water is present in the honey. Legal standards require honey to contain no more than 20% moisture to prevent fermentation. Beyond moisture testing, analysts perform pollen analysis to verify floral sources and geographic origin, which is important for regulatory labeling and for upholding claims like clover honey or orange blossom honey. Additional tests, such as electrical conductivity, help differentiate between nectar and honeydew honeys, while HMF levels, or hydroxymethylfurfural, are checked to ensure the honey hasn't been exposed to excessive heat during prior storage or transit. High-performance liquid chromatography may also be used to detect the presence of added sugars, which would indicate adulteration and result in immediate rejection of the batch. Once a drum passes inspection and is approved for processing, it is moved to the uncrystallization station. Raw honey can crystallize over time, particularly when stored in cooler environments or when the floral source is rich in glucose. Crystallized or partially crystallized honey must be reliquefied before it can be filtered or blended. This is achieved by placing the drums in heated chambers or warm water baths, known as hot rooms, where they are gently warmed to temperatures around 95 to 110 degrees Fahrenheit. This temperature range is sufficient to melt crystals without degrading the honey's delicate aromatic and enzymatic properties. Large facilities often use drum heating tunnels that can accommodate dozens of drums at a time. These tunnels employ radiant heat panels and convection fans that maintain a steady, uniform temperature throughout the enclosure. Temperature probes are inserted into each drum to ensure that internal temperatures rise slowly and evenly, preventing localized overheating which could darken the honey or degrade its quality. This gentle warming process can take anywhere from 24 to 72 hours, depending on the degree of crystallization and the initial temperature of the honey when it arrived. Now it's time to go into the liquefaction and transfer stage, where the now softened honey is pumped out of the drums and into the factory's primary processing line. This step requires specialized food-grade pumps capable of handling thick, sticky materials without introducing air bubbles or damaging the honey's texture. Positive displacement pumps, such as rotary lobe or progressive cavity pumps, are commonly used for this purpose. These pumps are designed to move viscous fluids at a steady rate without causing foaming or aeration, which can negatively impact downstream processing. As the honey is pumped from each drum, it passes through heated stainless steel pipelines that maintain a consistent temperature, usually around 110 to 120 degrees Fahrenheit, to keep the honey fluid during transit. The pipelines are insulated to minimize heat loss, and the entire system is cleaned between batches using CIP or clean-in-place systems, which circulate hot water and food-safe cleaning agents to maintain sanitary conditions. Valves and flow meters are used to control how much honey enters the next phase, which is usually a settling or holding tank. These tanks are large vertical silos equipped with gentle agitation paddles to keep the honey uniform without whipping air into it. At this stage, the honey is allowed to rest briefly, giving suspended particles like wax fragments, bee parts, or pollen clumps time to rise or settle. Some facilities incorporate slow-flow decanting chambers or skimming belts that remove surface foam and floating debris. The goal here is to prepare the honey for the critical filtration stage without exposing it to excessive agitation or temperature shifts, which could compromise quality. But up next is the filtration stage, one of the most technically controlled steps in factory honey processing. The challenge with filtering honey lies in removing impurities while preserving beneficial properties such as flavor, aroma, and trace pollen content. To accomplish this, processors use a series of progressively finer filters, starting with coarse metal mesh screens and moving to finer, micron-level filtration pads or cartridges. Initially, the honey flows through vibratory sieve filters or centrifugal strainers that remove large debris, including chunks of wax or bee remnants. These are often equipped with auto-cleaning screens that rotate or vibrate to prevent clogging. After coarse filtering, the honey enters a fine filtration system. Depth filters composed of cellulose or food-grade polypropylene are commonly used. These filters remove particles as small as 5 to 10 microns, including residual wax, dust, and crystallized sugar particles that could initiate recrystallization in the final product. To aid this process, the honey is maintained at a precise temperature of about 120 to 130 degrees Fahrenheit, warm enough to reduce viscosity and improve flow through filters, but not so hot as to destroy heat-sensitive enzymes or antioxidants. Inline temperature sensors and automated control panels ensure that every gallon of honey is processed under identical thermal conditions. Some advanced facilities even use vacuum-assisted filtration to further reduce the need for high temperatures, thereby preserving more of the honey's raw characteristics. Once filtration is complete, the honey is collected in large stainless steel blending tanks. These tanks are used to homogenize different batches of honey, standardize flavor profiles, and adjust final parameters such as color and clarity. Mixing paddles rotate at slow, controlled speeds to avoid aeration while ensuring a uniform blend. It's at this stage that some producers may add trace amounts of previously tested and approved batches to maintain flavor consistency across large volumes, especially if multiple floral sources are involved. Now it's time to explore the homogenization process in more detail, as this step plays a pivotal role in ensuring that every bottle or jar of honey pulled from the line is virtually identical in texture, color, and taste. Honey, being a natural product, can vary widely between batches due to differences in nectar sources, collection times, and even seasonal variations. To manage these inconsistencies, processors rely on computer-controlled blending protocols that match incoming honey against established reference standards. Before blending begins, technicians perform sensory and analytical testing on the batch, including color measurement using the Fund scale, which classifies honey from water white to dark amber. Flavor notes are assessed by trained sensory panels or electronic nose devices, while moisture and acidity levels are verified to determine blending ratios. If a batch is slightly darker than the standard product line, a portion of lighter honey is added to balance the color. If a batch is too viscous, a blend with a slightly higher moisture content is introduced to bring the final viscosity within specification. Mixing tanks used in this process are often jacketed with warm water or glycol to maintain the blending temperature at a steady 110 to 120 degrees Fahrenheit. Internal baffles guide the flow of honey, ensuring thorough integration without the formation of dead zones or stratification. The tanks are usually equipped with inline sensors that continuously monitor parameters like Brix, viscosity, and turbidity. The blending cycle may take several hours for large volumes, and throughout the process, automated samplers pull small amounts at regular intervals to verify that the blend remains within quality parameters. Once homogenization is complete, the honey is transferred to the final holding tanks that feed directly into the packaging lines. These tanks are placed on load cells that precisely measure the volume of honey dispensed into each container. From this point forward, the product must move through sealed, temperature-controlled systems to ensure no contamination occurs before bottling. And that leads directly into the highly synchronized packaging phase. As the homogenized honey flows from the final holding tanks into the packaging system, the entire process becomes a high-speed, tightly orchestrated sequence of mechanical precision and hygiene control. This stage is where the product begins to take on its final consumer-facing form, whether it's packaged in squeeze bottles, glass jars, tubs, or bulk containers. The packaging line starts with the selection and preparation of containers, which are fed into the system from large hopper units or depalletizers, depending on the container type. Plastic bottles often arrive pre-formed and stacked in bulk, while glass jars may come in pallets wrapped in protective plastic film. Regardless of material, every container goes through a rigorous cleaning phase before it is allowed anywhere near the honey. The first step in container preparation is an air rinse or ionized air cleaning process. Each container is inverted and passed through a chamber where blasts of filtered, pressurized air are directed inside. Ionized air is used specifically to neutralize any static charges that might cause dust or particles to cling to the sides of the container. In glass packaging lines, this process may be supplemented with a vacuum extractor that removes dislodged particles immediately after the air rinse. Some facilities also opt for a UV light exposure chamber that the containers pass through as an added antimicrobial safeguard. All of these steps are executed on automated conveyor systems, synchronized to keep pace with the fill line. Now it's time to go into the filling stage, which must be executed with extreme accuracy to ensure every package contains the correct weight or volume of honey. Honey's thick, slow-moving consistency makes it a challenging product to fill efficiently at scale. To meet this challenge, factories use volumetric piston fillers or gear pump filling machines, both of which are well suited for handling viscous, sticky products. These machines are equipped with heated nozzles and jacketed tubing to maintain the honey at an optimal temperature, typically around 110 degrees Fahrenheit, so it flows smoothly without foaming or dribbling. Each filling station is designed with multiple nozzles, often ranging from 4 to 16, depending on the line's speed and scale. The nozzles are programmed to descend into the containers during filling and retract as the level rises, a method known as bottom-up filling. This minimizes splashing and helps prevent the introduction of air bubbles, which can interfere with the product's shelf stability and aesthetic appearance. Inline check weighers are stationed just downstream of the filling heads, automatically rejecting any underfilled or overfilled containers from the line. Any deviation outside a narrow tolerance window triggers an immediate alert and mechanical removal. Immediately after filling, the containers are transferred to the capping and sealing station. For plastic bottles, this often involves a torque-controlled capper that applies precise rotational force to ensure a tight but not damaging seal. Flip-top caps, disc-top caps, or screw caps are automatically sorted and fed into place using vibratory feeders and cap chutes. In the case of glass jars, the capping process may involve steam vacuum sealing with metal lids, creating a hermetic seal that ensures freshness and shelf stability. As the lid is applied, a puff of steam is injected into the headspace, which condenses and creates a partial vacuum as the jar cools. Some packaging lines also include an induction sealing station. This involves placing a foil liner inside the cap, which is then sealed to the lip of the container using electromagnetic induction to heat and bond the foil to the rim. This creates a tamper-evident barrier that reassures consumers while also acting as an additional contamination safeguard. Once sealed, the containers pass through a water or air rinse to remove any stray honey drips from the filling station, followed by a drying tunnel that uses forced warm air to eliminate surface moisture before labeling. But up next is the labeling and coding process, where the honey finally begins to take on its retail-ready appearance. Labeling machines apply product labels at high speed using pressure-sensitive or shrink-sleeve labels, depending on the packaging format. Pressure-sensitive labels are peeled from a backing roll and applied to the container with rollers, while shrink-sleeve labels are wrapped around the container and heat-shrunk into place using a steam tunnel. Each label is applied with extreme precision using optical sensors that detect the exact placement zone, ensuring uniformity across all units. At this point, the line integrates the critical traceability step, date coding, and batch identification. Inkjet or laser coders are installed directly after the labeling station and are configured to print the production date, batch number, and expiration date onto the label, cap, or bottleneck. These codes are essential for tracking product back to its source in the event of a recall or quality issue, and they also help with inventory rotation throughout the supply chain. Vision systems verify the presence and legibility of these codes, and any container missing its code is automatically rejected from the line. Once labeled and coded, the honey containers move toward the secondary packaging phase. Here, they are grouped based on retail configuration, single bottles, multi-packs, or cartons, and loaded into larger corrugated cardboard cases. Robotic case packers or drop pack mechanisms handle this process with extreme care, particularly with glass containers, which require dividers and cushioning. Once the cases are assembled and filled, they're sealed using hot melt glue or tape and then passed through a check weigher to verify package weight consistency. The final stage in the packaging process is palletization, where filled cases are stacked in precise formations onto wooden or plastic pallets. Robotic palletizers equipped with vacuum grippers or mechanical arms lift and arrange the cases row by row, ensuring that weight is evenly distributed to prevent collapse during transport. Once the pallet is complete, it is wrapped with industrial stretch film to stabilize the load and protect it from moisture and dust. Each pallet receives a barcode label containing all relevant shipping and traceability data, including product type, quantity, destination, and handling instructions. Now it's time to go into the warehousing and distribution stage, which is vital to maintaining honey's shelf life and ensuring that product quality is preserved from the factory to the consumer. Honey is hygroscopic, meaning it absorbs moisture from the air, so warehousing conditions must be carefully controlled. Finished pallets are moved to temperature and humidity-controlled warehouse zones where the ambient environment is kept between 60 and 75 degrees Fahrenheit, with relative humidity below 60% to prevent moisture ingress that could lead to fermentation or spoilage. Inventory is managed using a warehouse management system that assigns each pallet a digital location code, tracks product age, and ensures first in, first out rotation. Automated guided vehicles or forklifts retrieve pallets based on shipping schedules, and every movement is recorded in a centralized database. This allows full traceability not just back to the packaging date, but all the way through blending batches and raw honey origins. If a quality issue were ever discovered post-shipment, the manufacturer could instantly identify and recall only the affected lot numbers. Before pallets leave the facility, they may undergo one final inspection. Logistics personnel verify that labels match the shipping documentation, confirm temperature logs for any time-sensitive products, and ensure that stretch wrapping and labeling meet the receiving distributor's requirements. Some retailers have specific palletization rules, like maximum stack height or barcode placement, that must be followed exactly to avoid supply chain disruptions. Once cleared, pallets are loaded into temperature-controlled trucks using dock levelers that ensure a smooth transition from warehouse to vehicle. These trucks are often equipped with sensors that track internal temperature and humidity levels during transit. If any threshold is breached during transportation, alerts are sent to the distribution center to allow preventive action. This step is critical because improper handling during shipping can undo months of careful processing. For instance, exposure to excessive heat can darken the honey, degrade its enzymes, and even trigger fermentation if the moisture content is borderline. As the honey moves through regional distribution centers and into retail outlets, it remains in sealed containers that shield it from light and air. Most honey has a shelf life of 2 years or more if stored properly, thanks to its low water activity and high sugar concentration, which naturally inhibit microbial growth. However, the quality and freshness perceived by the consumer are still closely tied to how well every part of the manufacturing and distribution process has been executed, from the bee to the bottle to the shelf. Every detail, every degree of heat, every micron of filtration, and every second of line timing plays a role in preserving the integrity of the final product. And even after it reaches store shelves, the story of how honey is made in a factory continues to resonate with precision, craftsmanship, and scientific control. To fully understand the industrial production of honey, it's important to go beyond the mechanics and explore the subtleties of product customization, regulatory compliance, and the final quality control processes that make factory-scale honey not just uniform, but legally marketable and consumer safe. After the honey has been packaged, palletized, and staged for distribution, another dimension of the process becomes active: the post-packaging quality assurance system. This system acts as a final safeguard to confirm that the product leaving the facility not only meets internal quality standards, but also complies with local, national, and international food safety laws. One of the most essential tasks during this final phase is the detailed sampling and archiving of batch samples. From each production lot, designated containers are pulled from the finished goods and sent to the factory's on-site analytical laboratory. These samples are catalogued, sealed, and retained in climate-controlled archives for up to several years, depending on regulatory requirements. This ensures that if a complaint, audit, or issue ever arises, the facility can test the retained sample and compare it to the current product in question. The archive system is tied directly into the facility's digital traceability records, allowing a sample to be matched instantly to the exact floral source. Filtration parameters, blend ratios, packaging date, and even which employee signed off on the batch. Parallel to this, comprehensive chemical and microbiological testing is performed on the pooled samples. Even though honey is naturally resistant to microbial growth due to its low water activity and high sugar content, every lot is still tested for yeast, mold, and spore-forming bacteria, such as Clostridium botulinum. The latter is especially critical for honey intended for infant consumption. Though honey is generally not recommended for children under 1 year of age, advanced polymerase chain reaction methods and microbial plating techniques are used in-house or sent to certified third-party labs for verification. The chemical testing regimen goes even deeper. In addition to previously mentioned standards such as moisture and HMF, tests are conducted to confirm that no contaminants have been introduced during packaging. This includes screenings for bisphenol A in plastic containers, phthalates, heavy metals like lead or arsenic, and residues from cleaning agents. Food-grade lubricants used in machinery are also tightly controlled to prevent incidental contact, and testing verifies their absence in finished products. Random bottles are sometimes subject to full shelf life simulation testing, where accelerated aging is used to project how the honey will behave under various conditions over time. Now it's time to go into the regulatory labeling and export compliance procedures, a crucial and often complex step for companies that ship honey across borders. Labeling is governed by a mixture of national food laws and international trade agreements. In the United States, for example, the Food and Drug Administration requires that honey be labeled with the common or usual name, net weight, ingredient list, the name and place of the business, and nutrition facts. Additional designations such as raw, organic, unfiltered, or wildflower must be substantiated with supply chain documentation and laboratory verification. For export to the European Union, labeling rules become even more intricate. The EU requires origin declarations if more than one country of origin is involved, meaning that a blend containing honey from, for example, Argentina and Canada must say, blend of honeys from more than one country, unless the exact percentages are broken down. Pollen analysis and isotopic testing are commonly used to verify the authenticity and origin of honey destined for the EU, and the entire production process must comply with the European Honey Directive. This includes ensuring that no heat treatment exceeds 40 degrees Celsius if the product is labeled as raw, and that no enzymatic activity is lost. The labeling department works in tandem with regulatory and export compliance officers, who maintain up-to-date databases of international standards, customs documentation, and product certifications. These certifications may include organic certificates, non-GMO verification, halal or kosher certification, fair trade documentation, and country-specific certifications of analysis. Every pallet destined for export is linked to a detailed manifest, and random audits ensure that the physical label matches its digital record in the product lifecycle database. Any discrepancy can halt a shipment and trigger a full traceability review. But up next is the specialization phase, where some facilities go beyond traditional honey and produce value-added variations to meet niche markets or changing consumer demands. This might include whipped or creamed honey, honey infused with natural flavors or botanical extracts, or honey blended with additives like royal jelly, bee pollen, or propolis. Each of these variations requires separate processing lines or batch scheduling to avoid cross-contamination and to comply with labeling laws that distinguish these products from standard filtered honey. Creamed honey, for example, requires controlled crystallization to achieve a smooth, spreadable texture. After filtration and homogenization, the honey is seeded with a small amount of finely crystallized honey and slowly stirred under cool temperatures in a creaming tank. This controlled environment allows microcrystals to form uniformly, resulting in a product that remains spreadable even when stored at room temperature. The tanks used in this process are jacketed with cooling fluid and fitted with slow-turning paddles that prevent the formation of large crystals. Flavored honey follows a different path. Natural flavor compounds such as cinnamon, ginger, vanilla, lemon, or even chili are emulsified into a small portion of honey before being slowly blended into the main batch. This ensures even distribution and prevents hotspots of flavor. Each additive must be food safe, approved by regulatory bodies, and tested for interaction with honey's enzymes and acidity. In some cases, additional filtration or viscosity adjustment is needed to maintain the same flow behavior in the bottling equipment. These specialty honeys are typically packaged in smaller volumes and targeted toward gourmet or health-conscious consumers. Manufacturing Almond Joy candy bars on an industrial scale begins long before any chocolate is melted or coconut is mixed. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components, the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then graded using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase, designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every Almond Joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for Almond Joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated. separated into single file and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking. And an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the Almond Joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit, and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor, and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the 1/10 of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coder, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable. Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coded, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final check weigher ensures that the total weight of each carton falls within specification, and the completed units are then moved down the line to case packing. The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermal loggers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from Coconut Grove to grocery store, can be completed in just a matter of weeks, but every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability, regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. Trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers. And the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final package. The manufacturing facilities are equipped with advanced machinery, precision-engineered systems, and rigorous quality controls. Each step in the process is optimized for efficiency, consistency, and the highest standards of food safety. In this detailed breakdown, we'll explore how Nutella is made inside a modern factory, from the raw materials to the final product, with a close look at the construction, operation, and technical aspects of the factory's systems and machinery. The process begins with the sourcing of raw ingredients, including hazelnuts, sugar, cocoa powder, palm oil, skim milk powder, and vanillin. These ingredients are delivered to Nutella factories in massive quantities, requiring large-scale handling infrastructure. Hazelnuts, one of the key components of Nutella, are often sourced from Turkey and Italy, two of the largest hazelnut producers in the world. Upon arrival at the factory, hazelnuts are stored in enormous silos or temperature-controlled storage rooms to maintain their freshness. The silos are made of food-grade stainless steel and designed to protect the nuts from humidity and contamination, while allowing for precise dispensing into the production line. The first step in processing the hazelnuts is cleaning. Hazelnuts arrive in bulk shipments, often mixed with debris such as shells, stems, and dirt. To address this, the factory uses a series of cleaning systems that include vibrating screens, air classifiers, and magnetic separators. The vibrating screens shake the nuts to separate them from larger debris, while the air classifiers blow away lightweight impurities like husks and dust. Magnetic separators are also used to detect and remove any metallic particles that might have entered the shipment during harvesting or transport. Once cleaned, the hazelnuts undergo visual inspection using high-speed optical sorting machines equipped with cameras and sensors. These machines identify and remove any defective hazelnuts, such as those with discoloration, cracks, or signs of mold. After cleaning, the hazelnuts move to the roasting stage. Roasting is a crucial step in developing the rich, nutty flavor that characterizes Nutella. In the factory, this is achieved using massive industrial roasting ovens. These ovens are designed with rotating drums or conveyor belts to ensure even roasting. The temperature is carefully controlled, typically ranging between 280 and 320 degrees Fahrenheit, depending on the size and moisture content of the hazelnuts. Sensors monitor the temperature and time to ensure consistency, as over-roasting can lead to bitterness, while under-roasting can result in a lack of flavor. The entire roasting process is automated, and the equipment is designed for continuous operation to handle the high volume of hazelnuts required for production. Once roasted, the hazelnuts are transferred to grinding machines. These machines are equipped with heavy-duty stainless steel blades and rollers that crush the nuts into a fine paste. The grinding process occurs in multiple stages, with each stage further reducing the particle size of the hazelnut paste. In the initial stage, the nuts are coarsely ground into a chunky paste. In the subsequent stages, the paste is refined into a smooth consistency, with particle sizes measuring less than 30 microns. This ultra-fine grinding is essential for achieving Nutella's creamy texture. The equipment used in this process, such as colloid mills and ball mills, is highly specialized and designed to operate under high pressure and at precise speeds. The resulting hazelnut paste is collected in large stainless steel tanks, where it is stored at a controlled temperature to preserve its flavor and consistency. While the hazelnut paste is being prepared, the other ingredients are processed in parallel. Sugar, which provides sweetness to Nutella, is delivered to the factory in bulk containers or tankers. Upon arrival, the sugar is unloaded into silos equipped with pneumatic conveying systems. These systems use air pressure to transport the sugar from the silos to the milling area, where it is ground into a fine powder. Industrial sugar mills are used for this purpose, and the grinding process ensures that the sugar particles are small enough to dissolve uniformly in the mixture. The factory also incorporates sieving systems to filter out any impurities or oversized sugar particles before they proceed to the blending stage. Cocoa powder, another key ingredient, undergoes a similar process. The cocoa powder is stored in sealed silos to protect it from moisture and contamination. Before being added to the Nutella mixture, the cocoa powder is sifted through vibrating screens to break up clumps and ensure a fine, even consistency. This step is crucial for achieving the smooth texture of the final product, as any clumps could create inconsistencies during blending. Palm oil, which gives Nutella its creamy consistency and prevents separation, is stored in large, temperature-controlled tanks. These tanks are equipped with heating elements to keep the oil in a liquid state, as palm oil tends to solidify at room temperature. The oil is pumped through insulated pipes to the mixing area, where it is carefully measured and added to the blend. The precise control of temperature and flow rate is essential to ensure that the oil integrates smoothly with the other ingredients. Skim milk powder, which adds a subtle dairy flavor and contributes to the creamy texture of Nutella, is stored in sealed containers or silos to prevent exposure to air and moisture. Before being used, the milk powder is sifted and screened to remove any lumps. Factories use advanced pneumatic conveying systems to transport the milk powder from the storage silos to the mixing area, ensuring that the ingredient is handled efficiently and hygienically. The blending process is the heart of Nutella's production, where all the prepared ingredients come together to form the final product. The blending tanks used in Nutella factories are massive, often with capacities of several thousand gallons. These tanks are equipped with high-speed agitators and temperature control systems. The hazelnut paste, sugar powder, cocoa powder, skim milk powder, palm oil, and vanillin are added to the tank in precise proportions, which are controlled by computerized dosing systems. These systems are programmed to weigh and dispense each ingredient accurately, ensuring consistency across batches. During blending, the mixture is heated slightly to help the ingredients combine more effectively. The temperature is carefully monitored, as excessive heat could alter the flavor and texture of the product. The blending tanks are designed to ensure even mixing, with agitators that create a vortex to incorporate all the ingredients thoroughly. The result is a homogeneous mixture with a smooth, creamy consistency. Once the blending process is complete, the mixture undergoes a refining stage. Refining is a critical step that ensures the final product is free of any graininess. The refining process takes place in multi-stage roller mills, which are equipped with heavy-duty steel rollers. These rollers apply immense pressure to the mixture, reducing the particle size of any remaining solids to less than 20 microns. This process not only enhances the texture of Nutella, but also improves its spreadability. The roller mills are fitted with precision sensors that monitor the pressure and temperature during refining, ensuring optimal performance. After refining, the mixture is transferred to the conching stage. Conching is a process borrowed from chocolate manufacturing and involves agitating the mixture in large, heated tanks for several hours. This process helps to further smooth the texture and enhance the flavor of the spread by allowing volatile compounds to evaporate and by evenly distributing the fats and solids. The conching tanks are equipped with paddles or rollers that knead the mixture continuously. The temperature and duration of conching are carefully controlled, as overconching could negatively affect the spread's consistency. The finished Nutella is then pumped into holding tanks, where it is kept at a controlled temperature until it is ready for packaging. These tanks are equipped with agitators to prevent separation and maintain the spread's uniformity. Before the Nutella is packaged, it undergoes a final round of quality control. Samples from each batch are tested for flavor, texture, color, and viscosity. The factory uses advanced laboratory equipment such as viscometers and spectrophotometers to ensure that the product meets the company's stringent standards. Any deviations from the desired specifications are identified and corrected before the product proceeds to the packaging stage. Packaging is the final step in Nutella's production process, and it is carried out with the same level of precision and efficiency as the earlier stages. The spread is pumped from the holding tanks into automated filling machines, which dispense precise amounts of Nutella into jars. The filling machines are equipped with high-speed nozzles that can fill hundreds of jars per minute. Each jar is made from food-grade plastic or glass and arrives at the factory pre-sterilized to ensure hygiene. The jars are sealed with tamper-proof lids, which are applied and tightened using automated capping machines. Once the jars are sealed, they are conveyed to labeling stations, where Nutella's iconic branding is applied. The labels include important information such as the lot number, production date, and expiration date, which are printed using high-speed inkjet or laser printers. After labeling, the jars are inspected by vision systems that check for defects such as misaligned labels or damaged seals. Any defective jars are automatically removed from the production line. The jars are then packed into cardboard cartons using robotic packing systems. These systems are programmed to arrange the jars in specific configurations to maximize space and protect the jars during transportation. The cartons are sealed and stacked onto pallets using robotic palletizers. The pallets are then wrapped in plastic film for stability and loaded onto trucks or shipping containers for distribution. The entire packaging process is designed for high efficiency, with minimal manual intervention and maximum output. Throughout the factory, automation plays a key role in maintaining efficiency and consistency. Programmable logic controllers and supervisory control and data acquisition systems are used to monitor and control every aspect of the production process. These systems provide real-time data on parameters such as temperature, pressure, and flow rates, allowing operators to make adjustments as needed. The factory is also equipped with advanced robotics and machinery that ensure smooth operation, from ingredient handling to final packaging. Hygiene and safety are top priorities in Nutella factories. Production areas are constructed with food-grade stainless steel surfaces and epoxy-coated floors that are easy to clean and sanitize. Air filtration systems maintain a clean environment by preventing airborne contaminants from entering critical zones. Employees follow strict hygiene protocols, including wearing protective clothing and washing their hands regularly. The factory is regularly inspected to ensure compliance with international food safety standards, guaranteeing that every jar of Nutella is safe for consumption. This intricate, highly automated process ensures that Nutella is consistently smooth, flavorful, and delicious, meeting the high expectations of its millions of fans worldwide. Every step, from the handling of raw ingredients to the final packaging, is a testament to the engineering and precision that go into creating this beloved spread. The result is a product that continues to delight consumers, one jar at a time. Peanut butter, a staple spread beloved worldwide for its creamy or crunchy texture, requires a sophisticated and highly organized manufacturing process to meet the demand for consistent quality and flavor. Behind every jar of peanut butter is an intricate factory process that starts with the raw peanuts and ends with precisely packaged jars ready for distribution. Let's take an in-depth look at the factory production process, exploring the machines, systems, and engineering techniques that make it all possible. The process begins with the sourcing of raw peanuts. These peanuts are typically grown in countries like the United States, China, India, and Argentina, which are among the largest producers of peanuts globally. Peanuts are harvested in vast quantities, cleaned and dried at their source before being shipped to peanut butter manufacturing facilities. Factories require a consistent supply of high-quality peanuts, and to ensure that the raw peanuts are often tested upon arrival for size, moisture content, and overall quality. This ensures only the best peanuts are used for processing. Upon arrival at the factory, peanuts are stored in massive silos or bins designed specifically for food products. These silos are constructed from food-grade stainless steel or coated steel to prevent contamination and ensure proper hygiene. Inside the silos, the peanuts are protected from moisture, pests, and temperature fluctuations. These storage systems are equipped with conveyor systems that efficiently transfer peanuts from the silos to the initial cleaning and processing stages. The first step in processing peanuts is cleaning. Even though peanuts are partially cleaned at their source, factories implement a rigorous cleaning process to ensure no foreign materials or impurities remain. Vibrating screens are used to remove debris such as dirt, stones, and small sticks. Air classifiers blow air through the peanuts to remove lighter debris such as peanut skins or husks. Magnets are also employed to extract any metallic impurities. Optical sorting machines equipped with cameras and sensors scan each peanut as it moves along a conveyor belt, automatically removing any defective peanuts, including those with discoloration, mold, or deformities. After the cleaning process, the peanuts proceed to the roasting stage. Roasting is a critical step in peanut butter production, as it develops the rich, nutty flavor that defines the final product. Factories use industrial roasting ovens to roast the peanuts at controlled temperatures. These ovens come in two main types: batch roasters and continuous roasters. Batch roasters are used for smaller production lines, while continuous roasters, which use conveyor belts to move peanuts through a heated chamber, are used for larger scale operations. The temperature in these roasters typically ranges from 300 to 350 degrees Fahrenheit. The roasting process is closely monitored with temperature sensors and automated control systems to ensure the peanuts are roasted evenly. If some peanuts are over-roasted, they can turn bitter, while under-roasted peanuts may lack flavor. The level of roasting can also be adjusted depending on whether the final peanut butter will have a mild or more robust taste. Once roasted, the peanuts are cooled to stop the cooking process. Cooling is achieved by passing the roasted peanuts through chambers with powerful fans or cool air blowers. This step is crucial because it prevents the peanuts from continuing to cook, which could lead to inconsistencies in flavor. Some factories also use a water spray system to rapidly cool the peanuts, though this is less common as it can add moisture to the product. The cooling systems are designed to operate continuously to keep pace with the output of the roasting ovens. With the peanuts roasted and cooled, the next step is to remove their skins and separate the kernels. Skin removal is done using blanching machines. These machines have rotating drums or abrasive rollers that rub the peanuts, causing the thin outer skin to flake off. Some systems use steam blanching, where the peanuts are exposed to high-pressure steam to loosen the skins before mechanical removal. After blanching, the peanuts pass through air classifiers that blow away the loose skins, leaving behind clean peanut kernels. Factories also use gravity separators to sort peanuts by size and density, ensuring that only uniform peanuts proceed to the grinding stage. Before grinding, the peanuts are inspected again for quality. This is done using high-speed optical sorters that ensure any remaining defective peanuts are removed. Factories often have automated weighing and proportioning systems at this stage to determine the exact amount of peanuts needed for each batch. This level of precision is crucial for maintaining consistency in the flavor and texture of the peanut butter. The grinding process is the heart of peanut butter production. The roasted peanuts are fed into industrial grinders, where they are crushed into a fine paste. This process happens in multiple stages, beginning with coarse grinding and followed by finer grinding. The equipment used for this includes hammer mills and roller mills, which are specifically designed to reduce the peanuts into small, uniform particles. In many factories, the particle size is reduced to less than 20 microns, which is smaller than the diameter of a human hair. Achieving such a fine consistency is essential for the creamy texture that many consumers expect from peanut butter. For crunchy peanut butter, the process is slightly different. In these cases, a portion of the peanuts is coarsely ground and set aside before the final blending stage. These larger peanut pieces are later mixed into the smooth paste to create the characteristic crunchy texture. To prevent the peanut butter from separating, stabilizers such as hydrogenated vegetable oils or palm oil are added during the grinding process. These oils help bind the natural peanut oils to the solid peanut particles, ensuring a smooth and stable product that doesn't separate in the jar. Salt and sugar are also added at this stage to enhance the flavor of the peanut butter. Factories use precision dosing systems to measure and add these ingredients in exact proportions, ensuring every batch has the same taste. After grinding, the peanut butter is sent through a mixing stage, where it is further blended in large stainless steel tanks equipped with high-speed agitators. This stage ensures that the stabilizers, salt, and sugar are evenly distributed throughout the peanut butter. These tanks are often heated slightly to keep the peanut butter at the right consistency for mixing. The temperature is carefully controlled, as overheating can alter the flavor or texture of the peanut butter. Once the mixing is complete, the peanut butter undergoes quality control checks. Samples from each batch are tested in an on-site laboratory for flavor, texture, and consistency. Advanced instruments, such as viscometers, are used to measure the viscosity of the peanut butter, ensuring it meets the desired standards. Factories also use particle size analyzers to confirm that the peanut butter's texture is smooth and uniform. These quality checks are critical, as even slight variations can impact the final product's appeal to consumers. The final step in the manufacturing process is packaging. The peanut butter is pumped from the mixing tanks to filling machines, where it is dispensed into jars. These filling machines are capable of handling thousands of jars per hour, ensuring high efficiency. The jars, typically made of food-grade plastic or glass, arrive at the factory pre-cleaned and are sterilized again before filling. The filling nozzles are designed to dispense precise amounts of peanut butter into each jar, ensuring uniform weight and volume. Once the jars are filled, they move to the capping machines, where tamper-proof lids are applied and tightened. After capping, the jars are conveyed to labeling machines, which apply the brand's signature labels, along with lot numbers and expiration dates for traceability. Vision systems inspect each jar to ensure that the labels are correctly applied and that there are no defects in the seals or packaging. The jars are then packed into cardboard boxes using robotic packing systems. These robots are programmed to arrange the jars in specific configurations to optimize space and protect the jars during transportation. The boxes are sealed and stacked onto pallets using automated palletizing systems. Finally, the pallets are wrapped in plastic film for stability and loaded onto trucks or shipping containers for distribution. Throughout the entire production process, automation plays a vital role in maintaining efficiency and consistency. Factories are equipped with programmable logic controllers, PLCs, and supervisory control and data acquisition, SCADA systems, that monitor and control every aspect of production. These systems provide real-time data on parameters such as temperature, pressure, and flow rates, allowing operators to make adjustments as needed. Robotic systems handle many tasks, from sorting and cleaning peanuts to packaging the final product, reducing the need for manual labor and ensuring precision. Hygiene and safety are also top priorities in peanut butter factories. The production areas are constructed with food-grade stainless steel surfaces and epoxy-coated floors that are easy to clean and sanitize. Positive air pressure systems prevent airborne contaminants from entering critical zones, while strict hygiene protocols ensure that employees maintain cleanliness throughout the production process. The entire facility is regularly inspected to comply with international food safety standards, ensuring that every jar of peanut butter is safe for consumption. Peanut butter production is a complex and highly technical process that relies on advanced machinery, precise engineering, and rigorous quality control. From the cleaning and roasting of peanuts to the grinding, mixing, and packaging of the final product, every step is designed to create a spread that is smooth, flavorful, and consistent. Factories operate with remarkable efficiency, producing thousands of jars per day to meet the global demand for this versatile and beloved product. Strawberry jam production is a fascinating and highly engineered process that combines precision machinery with time-tested techniques to create a smooth, fruity spread. At the core of this process are high-quality strawberries, sugar, pectin, and citric acid, all carefully handled and processed to achieve the perfect consistency and flavor. Inside a modern jam factory, every step is optimized for efficiency, consistency, and food safety. The process begins with the selection and delivery of fresh or frozen strawberries. Factories typically source strawberries from local farms or large-scale suppliers. Frozen strawberries are often preferred for large-scale production because they are preserved at peak ripeness, ensuring consistent flavor year-round. The strawberries arrive in bulk containers and are stored in cold rooms or freezers to maintain their quality until processing begins. Before entering the production line, the fruit undergoes a thorough cleaning process. This includes washing the strawberries in large tanks filled with filtered water, where gentle agitation removes dirt, debris, and any residual pesticides. Once cleaned, the strawberries pass through optical sorting machines. These machines use cameras and sensors to identify and remove defective or discolored fruit. Advanced systems can even detect minute imperfections, ensuring that only the highest quality strawberries make it into the jam. After sorting, the strawberries are sent to cutting or mashing machines, depending on the desired jam texture. For chunkier jams, strawberries are coarsely chopped, while for smooth spreads, they are mashed or pureed into a uniform consistency. The fruit then enters large stainless steel cooking kettles or continuous cooking systems. In these vessels, the strawberries are combined with sugar, which not only sweetens the jam, but also acts as a natural preservative. The sugar is added using automated dosing systems that measure precise quantities to ensure consistent flavor. Pectin, a natural thickening agent derived from fruit, is added to help the jam set. Citric acid is also incorporated to balance the sweetness and enhance the fruit's natural flavor. The mixture is slowly heated, with temperatures reaching up to 220 degrees Fahrenheit to activate the pectin and achieve the ideal gel-like consistency. During cooking, the jam undergoes constant agitation to prevent scorching and ensure even heating. Steam-jacketed kettles or vacuum cookers are often used, as they allow for rapid and uniform heating. Modern vacuum systems are particularly advantageous because they enable cooking at lower temperatures, preserving the fresh flavor and bright color of the strawberries. Throughout the cooking process, sensors monitor the temperature, pH levels, and viscosity of the jam, ensuring that the final product meets strict quality standards. Once the jam reaches the desired consistency, it is pumped through a series of filters to remove any seeds or large pieces if a smoother texture is desired. The finished jam is then transferred to filling machines. These machines dispense precise amounts of jam into sterilized glass jars or plastic containers. The jars are immediately sealed with tamper-proof lids to maintain freshness and prevent contamination. After sealing, the jars are passed through pasteurization tunnels, where they are briefly heated to destroy any remaining microorganisms. Finally, the jars are labeled, inspected, and packed into cartons using robotic packaging systems. The entire process is highly automated, ensuring efficiency and consistent quality, from the arrival of fresh strawberries to the delivery of jars to store shelves. This seamless blend of traditional cooking techniques and advanced technology ensures that every jar of strawberry jam is rich in flavor, perfectly textured, and safe for consumers to enjoy. Bananas begin their journey in the tropical plantations, where they are carefully cultivated to meet the demands of the global market. The process starts with the selection of optimal banana varieties, with Cavendish bananas being the most widely produced due to their durability and resistance to transportation stress. The banana plants, which are technically large herbs rather than trees, are cultivated in nutrient-rich soil under warm and humid conditions. Farmers carefully monitor the growth of banana plants, ensuring that they receive the right amount of water, nutrients, and protection from pests and diseases. Once the bananas reach the correct stage of maturity, typically around 9 months after planting, the harvesting process begins. Workers use sharp machetes or mechanical cutting tools to carefully cut the large banana bunches, which can weigh up to 50 kilograms. These bunches are placed onto conveyor systems or carried manually to avoid damage. Harvested bananas are quickly transported to centralized collection points, where they undergo a thorough sorting and initial quality inspection. Workers remove any damaged or overly ripe bananas, ensuring only the best quality fruit continues through the production process. The bananas are then washed in large water tanks, often infused with disinfectants to remove dirt, sap, and potential contaminants. This washing step also helps prevent the spread of diseases and fungi that could compromise the fruit's shelf life. Once cleaned, the bananas move onto grading stations, where they are categorized based on size, shape, and external appearance. Factory production standards dictate that only bananas meeting strict criteria proceed to the next stage. At this point, the bananas are separated from the large bunches into smaller clusters, typically consisting of 4 to 7 bananas. These clusters are cut with precision to maintain a uniform presentation. Automated machines or skilled workers carefully trim excess stems to the appropriate length, preventing damage during transportation and further processing. After trimming, the bananas are once again rinsed and placed onto conveyor belts, leading to the next stage of processing. Temperature control is crucial throughout the handling of bananas. To slow down ripening and ensure the fruit remains in peak condition, the bananas are placed in large cooling rooms set to around 13 to 15 degrees Celsius. These controlled conditions help preserve the bananas during transportation to industrial processing facilities, where they undergo further treatment, packaging, and preparation for global distribution. Bananas are highly perishable, so every step of the journey is carefully managed to maximize freshness. Once the bananas arrive at a dedicated processing facility, they undergo another round of inspections. Workers and automated sorting systems check for any defects that may have developed during transportation. The bananas are then placed into climate-controlled storage areas, ensuring that they do not ripen too quickly before packaging. Some bananas are destined for direct sale, while others will be processed into banana-based products such as dried bananas, banana puree, or banana chips. Each of these processing paths requires different equipment and techniques to achieve the desired final product. For fresh banana packaging, the fruit is arranged in trays or cartons designed to protect them from bruising. Packing lines employ automated machinery that gently places the bananas into their designated packaging, ensuring consistent weight and size in each package. Special padded trays or foam inserts are often used to cushion the bananas and minimize damage. The packaged bananas are then labeled, with stickers applied either manually or by automated applicators. These labels often include barcodes, brand names, and country of origin details. To extend shelf life and prevent premature ripening, some banana shipments are treated with ethylene inhibitors. These substances help slow down the natural production of ethylene gas, which is responsible for the ripening process. In cases where bananas need to ripen on demand, specialized ripening chambers are used at distribution centers. These chambers allow controlled exposure to ethylene gas, ensuring the bananas reach optimal ripeness just before being sent to retail stores. For bananas that will be further processed into products like banana chips, the production process involves additional steps such as peeling, slicing, and dehydration. High-speed peeling machines are used to remove the thick banana skins efficiently. The peeled bananas are then transported via conveyor belts to slicing machines, which cut them into uniform pieces based on the desired end product. These slices are then either fried in hot oil to create banana chips or placed in large dehydration ovens to produce dried banana snacks. The production of banana puree involves an entirely different set of machinery and techniques. After peeling, the bananas are mashed using industrial pulping machines, which break down the fruit into a smooth consistency. The puree is then passed through filtration systems to remove any fibrous material or unwanted particles. Depending on the intended use, the banana puree may undergo pasteurization, a heating process designed to kill bacteria and extend shelf life. The final product is then packaged in large containers or smaller, retail-friendly pouches. Throughout every stage of banana processing, quality control measures are strictly enforced. Automated sensors and human inspectors check for consistency in size, shape, color, and taste. Any defective or subpar bananas are removed from the production line and either repurposed for animal feed, compost, or other secondary uses. Ensuring food safety is paramount, and factories adhere to strict sanitation protocols to prevent contamination. Conveyor belts, slicing machines, and packaging stations are regularly cleaned and maintained to uphold hygiene standards. Once the bananas or banana-based products are ready for distribution, they are carefully loaded onto climate-controlled trucks or shipping containers. These vehicles maintain a stable temperature to prevent premature ripening or spoilage. The journey from processing facilities to retailers involves careful logistical planning, ensuring that consumers receive fresh, high-quality bananas at the right stage of ripeness. In cases where bananas are shipped internationally, advanced tracking systems monitor temperature conditions throughout transit, guaranteeing optimal quality upon arrival. Bananas destined for large-scale retail distribution often undergo one final quality check upon arrival at regional distribution centers. Here, ripening specialists assess the fruit's condition and determine whether ethylene gas exposure is necessary to accelerate the ripening process before shipment to supermarkets. Once the bananas reach grocery stores, they are displayed in carefully arranged sections to attract customers while minimizing handling damage. As the bananas move through the processing facility, their journey continues with additional quality control measures. Every banana that passes through the system is subject to strict oversight to ensure it meets the standards set by global markets. Some bananas are set aside for immediate export, while others are prepared for processing into various banana-based products. Each batch is tracked using barcodes or digital systems to maintain traceability, allowing factories to monitor their origins and ensure compliance with regulatory requirements. Bananas that are destined for further processing must first undergo additional cleaning. Large industrial washers use gentle streams of water combined with food-safe sanitizers to remove any remaining residues from the outer peel. For bananas that will be processed into products requiring peeled fruit, high-efficiency peeling machines are employed. These machines operate with incredible precision, using rotating blades and suction systems to remove the thick banana skin without damaging the soft fruit inside. The peeled bananas are then conveyed along sanitized belts toward the next stage of production. For bananas intended for drying, the peeled fruit is sliced into uniform pieces using high-speed industrial slicers. These slicers can be adjusted to produce different thicknesses depending on the desired final texture of the dried product. Once sliced, the banana pieces are spread out evenly on large drying trays or conveyor belts, ready to enter specialized dehydration chambers. The drying process typically involves controlled exposure to warm air, which removes moisture while preserving the fruit's natural sweetness. The temperature and humidity levels are carefully monitored to ensure the bananas do not become too brittle or lose their natural flavor. Depending on the facility, some manufacturers may opt for freeze-drying techniques, which use a vacuum process to extract moisture while retaining the fruit's structure and nutrients. Banana chips, a popular snack food, require a different production approach. Instead of dehydration, the sliced bananas are deep-fried in vegetable oil at high temperatures. Large industrial fryers are used to ensure an even cooking process. The frying time is precisely calibrated to achieve a crisp texture without overcooking or burning the banana slices. Some manufacturers enhance the chips by seasoning them with salt, sugar, or other flavorings before they are packaged. Excess oil is removed using centrifugal draining machines, which spin the banana chips to ensure a light and crispy texture. Banana puree production follows another distinct processing pathway. After peeling, the bananas are mashed in large industrial pulping machines. These machines use rotating blades or rollers to break down the fruit into a smooth, consistent mixture. To prevent oxidation and maintain the puree's natural yellow color, antioxidants such as ascorbic acid are often added during this stage. The banana puree is then subjected to pasteurization, where it is heated to a controlled temperature to kill any harmful microorganisms while preserving its nutritional content. Pasteurization is critical for extending the shelf life of banana puree, making it suitable for use in baby food, smoothies, and baking applications. Once the puree has been properly treated, it is packaged in large industrial containers, aseptic pouches, or smaller retail-friendly jars, ready for distribution. Every stage of banana processing requires stringent hygiene controls. Factories implement rigorous sanitation protocols, ensuring that all equipment, conveyor belts, and processing surfaces are regularly cleaned and sterilized. Workers involved in banana handling follow strict hygiene guidelines, wearing protective gloves, hairnets, and sanitized uniforms to prevent contamination. Automated monitoring systems continuously track environmental conditions, ensuring that temperature, humidity, and air quality remain within optimal ranges. Once processed, bananas and banana-derived products are carefully packed to prevent damage and preserve freshness. For fresh bananas, packing stations use automated sorting machines that place the fruit into protective cartons, ensuring uniform weight and size distribution. Banana chips are packaged using nitrogen-flushed bags to prevent oxidation and maintain crispness. Dried bananas and banana puree are sealed in airtight containers, minimizing exposure to moisture and contaminants. Packaging materials are chosen for their durability, ensuring that products remain intact throughout transportation and storage. After packaging, the bananas are prepared for distribution. Fresh bananas are loaded into climate-controlled shipping containers that maintain a stable temperature between 13 and 15 degrees Celsius, preventing premature ripening. These containers are equipped with ventilation systems that regulate air composition, ensuring optimal freshness upon arrival at their destination. Processed banana products follow a different logistics chain, with dried bananas, chips, and puree being transported in standard freight containers under controlled storage conditions. Ripening facilities play a crucial role in the banana supply chain. Upon arrival at distribution centers, fresh bananas may be placed into specialized ripening rooms, where controlled amounts of ethylene gas are introduced. Ethylene is a natural plant hormone that triggers the ripening process, allowing bananas to develop their characteristic yellow color and sweet flavor. Ripening rooms are carefully monitored, with temperature and humidity levels adjusted to ensure uniform ripening without over-ripening or spoilage. Once the bananas reach the desired ripeness, they are shipped to supermarkets, where they are displayed for consumers. In modern banana factories, automation is increasingly integrated into the production process. Advanced robotic systems handle delicate fruit with precision, minimizing bruising and maximizing efficiency. Optical sensors analyze banana quality, sorting them based on color, size, and ripeness. Conveyor belt systems are equipped with real-time monitoring technology, allowing factory managers to track production rates and detect potential issues before they impact output. The integration of data analytics and machine learning further enhances production efficiency, optimizing banana processing workflows based on demand trends and supply chain logistics. Sustainability is also a growing focus in banana manufacturing. Many factories implement eco-friendly initiatives to reduce waste and energy consumption. Banana peels and rejected fruit are repurposed as organic compost, animal feed, or biofuel. Some facilities incorporate solar panels and energy-efficient machinery to lower their carbon footprint. Water recycling systems help minimize water usage, ensuring that banana processing remains environmentally responsible. Efforts to improve fair trade practices and support banana farmers have also gained traction, ensuring ethical and sustainable sourcing of raw materials. Banana production is a complex and highly coordinated process that involves multiple stages of handling, processing, and distribution. From the moment bananas are harvested on plantations to the point where they reach consumers as fresh fruit or processed products, every step is meticulously managed to maintain quality, safety, and efficiency. Advances in technology continue to refine banana processing methods, making it possible to deliver high-quality bananas and banana-based products to markets worldwide. As the banana industry evolves, manufacturers continue refining their processes to improve efficiency, reduce waste, and maximize product quality. The journey from banana plantations to industrial processing facilities is a highly orchestrated operation, involving both traditional agricultural techniques and cutting-edge automation technologies. At every stage, from harvesting to packaging, strict protocols are followed to ensure that only the highest quality bananas make it to market. Once bananas have been harvested and sorted, those destined for industrial processing are transported in specialized containers to prevent damage. The journey from the plantation to the factory is carefully managed, with transportation schedules optimized to reduce delays and prevent premature ripening. Bananas that arrive at the factory in a raw state are first subjected to an additional round of inspections. Quality control teams examine each shipment, ensuring that the fruit meets the necessary criteria before it proceeds to the next stage. Upon arrival at the processing facility, bananas undergo a pre-treatment phase. This begins with a thorough cleaning process, where the fruit is washed in large, food-grade water baths. These washing stations are equipped with high-powered jets that remove any residual dirt, pesticides, or surface contaminants. Some factories add mild disinfectants or organic sanitizing agents to the water to eliminate bacteria and fungi that could affect the final product's shelf life. Once washed, the bananas are conveyed to sorting lines, where automated systems use sensors to categorize them based on size, ripeness, and surface quality. For fresh banana packaging, the bananas that meet industry standards are arranged into clusters and gently placed into protective cartons. Advanced robotic arms are sometimes used to handle the fruit, ensuring minimal human contact and reducing the risk of bruising. Packaging lines use precision weighing systems to guarantee uniformity in product distribution. Some packaging facilities use modified atmosphere packaging, where the oxygen levels inside the packaging are carefully controlled to slow down the ripening process. Bananas that are set aside for further processing move to dedicated peeling stations. Peeling bananas on an industrial scale requires specialized machinery that can efficiently remove the thick outer skin while preserving the soft interior. High-speed mechanical peelers use a combination of cutting blades and suction mechanisms to remove the peel in a single motion. For certain banana-based products, additional peeling techniques are employed, such as steam-assisted peeling, where a rapid blast of steam loosens the peel before mechanical separation. Once peeled, the bananas are inspected again to remove any that are overly bruised or damaged. The peeled bananas are then directed to their respective processing lines based on the final product they will be used for. Bananas designated for puree production are immediately transported to industrial mashing machines, where they are blended into a smooth consistency. These machines operate at high speeds, using rotating blades or pressure systems to break down the fruit into a fine pulp. To maintain the puree's natural color and prevent oxidation, citric acid or ascorbic acid may be added. The puree is then filtered to remove any fibrous material or unwanted solids, ensuring a smooth and consistent texture. Bananas intended for drying are sliced using automated slicing machines that produce even, uniform pieces. These banana slices are then placed onto mesh conveyor belts, which carry them through drying tunnels. The drying process varies depending on the manufacturer, but it typically involves controlled exposure to warm air at temperatures between 50 and 70 degrees Celsius. This gradual dehydration process removes moisture while preserving the natural sugars in the fruit, resulting in a sweet and chewy texture. Some manufacturers opt for freeze drying, which involves rapidly freezing the banana slices before placing them in a vacuum chamber to remove moisture. This method helps retain more of the banana's original flavor and nutritional content. Banana chips, a widely popular snack, undergo a frying process to achieve their crispy texture. The peeled bananas are first cut into thin slices before being submerged in large vats of hot vegetable oil. The frying process takes only a few minutes, during which the banana slices turn golden brown and develop their characteristic crunch. After frying, excess oil is removed using centrifugal draining machines, which spin the chips at high speeds to eliminate any remaining grease. To enhance flavor, the banana chips may be lightly salted, sweetened with honey, or coated in flavored seasonings before being packaged. Throughout every stage of production, factories implement rigorous quality control measures to ensure food safety and consistency. Optical scanners and high-speed cameras are used to detect imperfections, sorting out any defective bananas or banana products. Workers in food safety laboratories conduct regular microbial testing, checking for bacteria, yeast, and mold that could compromise product quality. Metal detectors and X-ray machines scan packaged products for any foreign contaminants before they are cleared for distribution. The final stage of banana processing involves packaging and storage. Fresh bananas are packed in ventilated cartons that provide airflow to regulate ripening. Banana chips and dried banana products are sealed in airtight packaging to maintain freshness and prevent moisture absorption. Banana puree is packaged in sterile, food-grade containers, which are often vacuum sealed or heat treated to ensure an extended shelf life. In large-scale food manufacturing, bulk containers of banana puree may be shipped to other processing facilities, where they are used in products such as baby food, smoothies, yogurt, and baked goods. Once packaged, the banana products are stored in climate-controlled warehouses before being transported to retailers and distribution centers. Logistics teams carefully plan shipping routes to minimize transit time and ensure that the products arrive in optimal condition. Fresh bananas are typically shipped in refrigerated trucks or containers, where the temperature is carefully regulated to prevent premature ripening. Ripening centers at distribution hubs monitor the banana's condition, exposing them to controlled amounts of ethylene gas when necessary to trigger the final ripening process before they reach grocery store shelves. Banana factories continuously innovate to improve efficiency and sustainability. Many facilities have adopted eco-friendly initiatives to reduce waste and energy consumption. For instance, banana peels and other byproducts from the production process are repurposed as compost, livestock feed, or biofuel. Some factories incorporate water recycling systems, filtering and reusing water from the washing process to minimize resource consumption. The use of solar energy and other renewable power sources is also becoming more common in banana processing plants, helping to reduce the industry's overall carbon footprint. The integration of smart technology and automation is revolutionizing banana production. Artificial intelligence, AI, and machine learning algorithms are used to optimize sorting, detect defects, and predict supply chain trends. Advanced robotics are being implemented to handle delicate fruit more efficiently, reducing human labor costs while increasing processing speeds. Data analytics tools allow factory managers to track production in real time, making adjustments to improve efficiency and reduce waste. The demand for banana-based products continues to grow, driven by consumer preferences for healthy, natural snacks and ingredients. Banana processing plants are expanding their product offerings to include innovative items such as banana flour, banana-based protein bars, and freeze-dried banana snacks. The industry is also focusing on sustainable sourcing, ensuring that bananas are grown using environmentally responsible farming practices that support fair wages and ethical labor conditions for workers. As the banana industry expands, factories are continuously developing new techniques to optimize efficiency, reduce waste, and maintain high product quality. The production cycle is carefully monitored, from the moment bananas are harvested in plantations to their transformation into various consumer products. Each stage is executed with precision to meet global market demands while ensuring sustainability and food safety. Once fresh bananas have been sorted, cleaned, and prepared for processing, the next step depends on their intended use. Some bananas will be packaged for fresh consumption, while others will be transformed into banana puree, dried banana products, or banana-based ingredients used in food manufacturing. For fresh bananas, factories implement protective packaging solutions to prevent bruising and ensure that the fruit remains in excellent condition throughout transportation and storage. These packaging solutions may include cushioned cartons, foam inserts, or breathable plastic wraps that regulate moisture levels and slow down ripening. Fresh bananas are often shipped in refrigerated trucks that maintain a stable temperature of around 13 to 15 degrees Celsius. This temperature range is crucial as it prevents premature ripening while keeping the fruit firm and fresh. Advanced logistics tracking systems monitor temperature fluctuations in real time, ensuring that bananas are transported under optimal conditions. If temperatures rise too high during transit, the bananas may ripen too quickly, leading to shorter shelf life and increased waste. Conversely, if temperatures drop too low, chilling injury can occur, causing the bananas to develop brown or black spots and compromising their quality. For bananas that undergo further processing, the industrial peeling phase is a critical step. While some banana-based products require manual peeling, most large-scale factories use specialized peeling machines to remove the thick banana skins efficiently. These machines operate using rotating blades or suction systems, ensuring that the fruit is peeled quickly and cleanly. In some cases, banana peels are softened using a brief steam treatment before being mechanically separated from the fruit. This method helps reduce waste and increases the yield of usable banana flesh. Once peeled, the bananas must be processed quickly to prevent oxidation, which can cause them to turn brown. For banana puree production, the peeled bananas are immediately transferred to high-speed pulping machines. These machines use rotating metal drums with fine mesh screens to break down the fruit into a smooth, uniform puree. The puree is then passed through filtration systems to remove any unwanted fibers or solid particles. To maintain color and flavor, natural antioxidants such as citric acid or ascorbic acid are added. Some manufacturers also incorporate mild pasteurization, heating the puree to a controlled temperature to eliminate bacteria and extend shelf life without compromising nutritional value. The banana puree is then packaged in aseptic containers, ensuring that it remains free from contamination. In some cases, the puree is concentrated by removing excess water, creating a thicker, more versatile product used in baby food, baked goods, and smoothies. The concentrated puree is typically stored in large industrial drums or vacuum-sealed pouches before being distributed to food manufacturers worldwide. For dried banana production, the peeled fruit is sliced into uniform pieces using precision slicing machines. These machines ensure that each banana slice maintains a consistent thickness, which is essential for even drying. The banana slices are then arranged on conveyor belts or drying racks, ready to enter industrial dehydration chambers. The drying process varies depending on the manufacturer and the intended final product. Traditional air drying methods involve exposing the banana slices to warm, circulating air at temperatures between 50 and 70 degrees Celsius. This gradual drying process removes moisture while preserving the fruit's natural sweetness and texture. Some manufacturers use freeze drying, a technique that involves freezing the banana slices and then placing them in a vacuum chamber. The vacuum removes moisture without subjecting the fruit to heat, resulting in a crisp, lightweight product that retains more of the banana's original nutrients and flavor. For banana chips, the production process is slightly different. Instead of drying, the banana slices are submerged in hot vegetable oil and fried until they develop a crunchy texture. Large industrial fryers maintain a consistent oil temperature, ensuring even cooking and a uniform golden brown color. After frying, excess oil is removed using centrifugal draining machines, which spin the chips at high speeds to extract any remaining grease. Some manufacturers apply additional flavoring, such as salt, sugar, cinnamon, or honey glaze, before packaging the banana chips in airtight bags to preserve freshness. Throughout the processing stages, factories implement strict food safety and quality control measures. Automated sorting systems use high-resolution cameras and optical sensors to inspect banana slices, puree, and chips for consistency in color, size, and texture. Any defective or substandard products are removed from the production line. Metal detectors and X-ray scanners check packaged banana products for potential contaminants, ensuring that every item meets the required safety standards before it reaches consumers. Banana factories also prioritize waste reduction and sustainability. Peels and other organic byproducts from the production process are repurposed in various ways. Some factories use banana peels as livestock feed, while others process them into compost or biofuel. Advanced waste management systems help minimize environmental impact, with some manufacturers investing in water recycling technologies to reduce water consumption during the cleaning and washing stages. As consumer demand for banana-based products grows, factories continue to innovate and expand their offerings. Beyond traditional banana puree, chips, and dried bananas, manufacturers are exploring new product categories, including banana flour, pre-packaged banana smoothie blends, and high-protein banana bars. Banana flour, made by grinding dried bananas into a fine powder, is gaining popularity as a gluten-free alternative for baking and cooking. This versatile ingredient is used in everything from bread and pancakes to energy bars and nutritional supplements. Banana processing facilities also invest heavily in automation and smart technology to improve efficiency. AI-powered sorting machines analyze banana quality in real time, adjusting processing parameters to optimize output. Robotic arms are increasingly used for packaging, reducing the need for manual handling and minimizing product damage. Real-time data analytics help factory managers monitor production performance, identify inefficiencies, and implement improvements that enhance productivity and reduce costs. The global banana industry relies on a well-coordinated supply chain to ensure that fresh and processed bananas reach consumers in peak condition. Distribution networks are carefully managed, with warehouses and ripening centers strategically located near major markets. Retailers use advanced inventory management systems to track banana shipments and predict demand, ensuring that stores remain stocked with fresh bananas while minimizing waste. In ripening centers, fresh bananas undergo controlled ethylene exposure to accelerate ripening before they are sent to supermarkets. The timing of this ripening process is critical, as it determines the banana's appearance and texture upon reaching store shelves. Ethylene gas concentrations, temperature, and humidity are carefully regulated to achieve uniform ripening without over-ripening or spoilage. Banana factories continue to evolve, integrating the latest advancements in food technology, sustainability, and logistics. As consumer preferences shift toward healthier and more sustainable food choices, the banana industry is adapting by offering organic, fair trade, and minimally processed banana products. These initiatives ensure that banana production remains both economically viable and environmentally responsible, meeting the needs of a growing global population while reducing the industry's ecological footprint. The meticulous handling of bananas throughout their journey from plantation to processing facility ensures that they maintain their freshness and quality, whether they are destined for fresh consumption or further industrial processing. The seamless transition between these stages requires advanced logistical coordination, as bananas must be transported quickly to prevent over-ripening while maintaining optimal storage conditions. Once inside the processing facility, each banana undergoes a series of treatments tailored to its final intended use. Bananas that are meant for fresh sale are carefully packaged in protective cartons, but the process doesn't end there. These fresh bananas are often stored in climate-controlled warehouses, where specialized ripening chambers help regulate their maturation. Since bananas ripen naturally through the release of ethylene gas, these chambers provide a controlled environment where ethylene exposure is adjusted based on shipment schedules. This process ensures that bananas arrive at supermarkets at the perfect stage of ripeness, ready for consumers to purchase. The ripening rooms are monitored with precision sensors that measure humidity, temperature, and gas concentration, ensuring that no batch over-ripens or becomes too soft before reaching store shelves. Meanwhile, for bananas destined for further processing, their journey involves a more intensive transformation. Once peeled using specialized machinery, these bananas are quickly moved into processing lines to prevent oxidation, which can lead to undesirable browning and flavor changes. Depending on their end use, the bananas are either mashed into puree, sliced for drying, or prepared for frying into banana chips. Banana puree production requires high-speed pulping machines that use stainless steel blades to break down the fruit into a smooth consistency. These machines operate in continuous production lines, with the puree moving through filtration systems that remove any unwanted fibers, seeds, or imperfections. The temperature of the puree is maintained at controlled levels to preserve its natural sweetness and prevent microbial growth. Some manufacturers incorporate flash pasteurization, a brief but effective heat treatment to extend the puree's shelf life without compromising flavor or nutritional value. The final product is then stored in sterilized tanks before being packaged in either small retail pouches or industrial-sized drums for bulk distribution. For dried banana products, the process is slightly different. Once peeled, bananas are fed into high-precision slicing machines that ensure each piece is uniform in size and thickness. The slices are then transferred to conveyor systems that guide them through dehydration chambers, where controlled airflow and heat gradually remove moisture from the fruit. This drying process can take several hours, depending on the desired texture and final moisture content of the product. Some manufacturers use vacuum drying or freeze drying techniques to enhance texture and retain more nutrients. These methods help produce crisp, long-lasting banana snacks that remain shelf-stable for extended periods. In banana chip production, the peeled and sliced bananas are submerged in industrial frying vats filled with hot vegetable oil. These vats operate at precise temperatures to ensure the banana slices fry evenly, developing a golden brown crispiness without burning. After frying, excess oil is removed using high-speed centrifugal drying machines, which spin the chips rapidly to eliminate residual grease. Some manufacturers season the chips immediately after frying, using automated sprayers to apply salt, sugar, or various flavor coatings. The finished banana chips are then transported to packaging stations, where they are sealed in airtight bags to preserve their crunch and prevent oxidation. Throughout the entire banana processing workflow, factories implement stringent quality control measures. Automated vision systems equipped with high-resolution cameras inspect banana slices, puree, and chips for consistency in size, color, and texture. Any substandard products are diverted from the main production line and repurposed for secondary uses such as animal feed or composting. Metal detectors and X-ray scanners provide additional safety checks, ensuring that no foreign contaminants are present in the final packaged products. The packaging process itself is highly automated, with conveyor belts guiding products into pre-measured containers. Fresh bananas are placed in breathable cartons that allow for ventilation, while banana chips and dried banana slices are packaged in nitrogen-flushed bags that prevent oxidation and extend shelf life. For banana puree, aseptic packaging methods are used to maintain product freshness without the need for refrigeration. Some large-scale food manufacturers purchase banana puree in bulk containers, which are then integrated into their own production lines for making baby food, desserts, and bakery items. Once packaged, banana products must be stored and distributed efficiently. Climate-controlled warehouses maintain optimal conditions for each type of banana product, ensuring that fresh bananas do not ripen too quickly and that processed banana items remain stable. Logistics teams coordinate shipments using real-time tracking systems, optimizing delivery routes to minimize transportation times and ensure products arrive in peak condition. Fresh bananas are often transported in refrigerated containers that maintain a consistent temperature, preventing premature ripening. These containers are equipped with ventilation controls that regulate humidity and air composition, ensuring that bananas remain firm and resistant to bruising during long-distance transit. Upon arrival at distribution centers, these bananas undergo a final ripening stage, where ethylene exposure is carefully managed to achieve the perfect color and texture before they are shipped to grocery stores. Banana-based products, such as chips, dried bananas, and puree, follow a slightly different distribution model. Since these products have longer shelf lives, they are often stored in dry warehouses before being shipped to retail stores or food manufacturers. These warehouses use advanced inventory management systems to track stock levels and prevent overproduction, ensuring a steady supply chain without excessive waste. The sustainability aspect of banana processing is a growing focus for manufacturers. Many factories have adopted eco-friendly initiatives to reduce their environmental impact. Banana peels and other organic byproducts are repurposed in various ways, such as being converted into animal feed, biofuel, or compost for agricultural use. Some facilities implement water recycling systems to minimize waste in the washing and processing stages, ensuring that water usage remains efficient. Additionally, energy-efficient machinery and solar-powered production plants are becoming more common, helping factories reduce their overall carbon footprint. In recent years, consumer demand for ethically sourced and organic bananas has driven changes in banana processing. More factories are adhering to fair trade standards, ensuring that banana farmers receive fair wages and that environmentally sustainable farming practices are followed. Organic banana production eliminates synthetic pesticides and fertilizers, requiring stricter handling protocols to maintain certification standards. These organic bananas go through the same processing methods, but must be kept separate from conventionally grown bananas throughout the supply chain to maintain their organic status. Technology continues to revolutionize banana processing, with artificial intelligence and automation playing an increasing role. AI-driven quality control systems analyze bananas for defects with greater accuracy than human inspectors, reducing waste and improving overall efficiency. Automated robotic arms handle delicate bananas with precision, ensuring minimal bruising during sorting and packaging. Data analytics software optimizes supply chain logistics, predicting demand patterns and helping factories adjust production schedules to meet market needs. The efficiency of banana processing factories relies on a combination of cutting-edge automation, rigorous quality control, and sustainable practices. From the moment bananas enter the facility to their final packaging and distribution, every step is carefully designed to maximize freshness, preserve nutritional value, and minimize waste. While fresh bananas undergo controlled storage and ripening processes to ensure peak quality upon arrival at retail stores, processed banana products like puree, chips, and dried slices follow more complex manufacturing pathways requiring specialized equipment and techniques. One of the critical elements of banana processing is maintaining the delicate balance between speed and quality. Since bananas are highly perishable, factories must operate with precision to prevent spoilage and ensure that only the highest quality fruit is used. Advanced sorting lines use a combination of human inspection and artificial intelligence-driven sensors to evaluate bananas based on their color, size, firmness, and surface condition. High-resolution cameras scan each banana as it moves along conveyor belts, identifying bruises, blemishes, or irregularities that could affect product quality. Any substandard bananas are automatically diverted to secondary processing lines where they may be repurposed for animal feed, composting, or biofuel production. For fresh banana packaging, factories utilize automated systems that gently place bananas into protective cartons or plastic trays. Each package is weighed to ensure consistency, with advanced robotic arms adjusting the number of bananas per carton if necessary. The packaging materials are designed to provide adequate ventilation while minimizing physical damage during transportation. Some factories also use biodegradable or recyclable packaging solutions, aligning with global sustainability trends and reducing plastic waste in the supply chain. Bananas that undergo further processing are peeled using high-speed peeling machines, which separate the edible fruit from its thick outer skin with remarkable efficiency. The peeled bananas are then subjected to additional cleaning, where they are rinsed in purified water infused with mild food-grade sanitizers to eliminate any remaining contaminants. Once cleaned, the bananas are directed toward their designated production lines based on the final product requirements. Banana puree production requires industrial-scale pulping machines, which operate using rotating blades or pressure-based extraction methods to break down the fruit into a uniform consistency. These machines are engineered to handle large volumes of bananas per hour, ensuring continuous output without interruptions. To prevent the puree from oxidizing and developing an undesirable brown hue, factories introduce natural preservatives such as lemon juice or ascorbic acid. The puree then undergoes pasteurization, a crucial step that involves briefly heating the product to eliminate harmful microorganisms while preserving its fresh taste and nutritional content. After pasteurization, the banana puree is rapidly cooled and transferred into sterilized storage tanks or aseptic packaging containers. For dried banana production, the peeled fruit is carefully sliced into even round or strips using precision cutting machines. The sliced bananas are then arranged on large drying trays or mesh conveyor belts that transport them through industrial dehydration chambers. These chambers use controlled heat and airflow to gradually reduce the moisture content of the bananas while retaining their natural sweetness. The drying time varies based on the desired texture, with chewy dried bananas requiring slightly higher moisture retention than crispy banana chips. Some manufacturers opt for vacuum drying or freeze drying methods, which help preserve the banana's original structure, flavor, and nutrient profile more effectively than conventional drying techniques. Banana chip production follows a different path, involving deep frying to achieve a crunchy texture. Once sliced, the banana pieces are fed into large capacity frying vats filled with hot vegetable oil. The frying process lasts only a few minutes, during which the natural sugars in the bananas caramelize, enhancing their sweetness and contributing to their golden brown appearance. Once fried, the banana chips are rapidly cooled and transferred to centrifugal drying machines, which remove excess oil and ensure a light, crisp finish. Some manufacturers add flavor enhancements such as cinnamon, honey, or even spicy seasonings before sealing the chips in airtight packaging. Quality control is a non-negotiable aspect of banana processing. Each production batch is subjected to multiple layers of testing, ensuring compliance with food safety regulations and consumer expectations. Optical scanners analyze banana slices and puree for consistency in texture and color, while microbial testing ensures that products remain free from harmful bacteria, yeast, and mold. Factories also employ metal detection and X-ray inspection systems to identify any potential foreign contaminants before the products are packaged and shipped. The packaging stage is highly automated, with conveyor belts guiding banana products into their respective containers. Fresh bananas are packed in ventilated cartons that allow for sufficient airflow, ensuring gradual ripening without over-ripening. Banana puree is sealed in vacuum-packed pouches or bulk-sized aseptic containers, which protect the product from oxidation and contamination. Dried bananas and banana chips are packaged in moisture-proof bags filled with nitrogen gas to prevent oxidation and preserve crispness. Once packaged, banana products are moved to temperature-controlled storage areas before distribution. Fresh bananas are carefully stored in ripening chambers at distribution centers, where ethylene gas exposure is calibrated to trigger controlled ripening before shipment to supermarkets. This process ensures that bananas reach store shelves at the perfect stage of ripeness, allowing consumers to enjoy them at their peak. For banana-based processed products, distribution logistics involve coordination between factories, warehouses, and retailers. Bulk banana puree shipments are often sent to food manufacturers, where they are used as ingredients in smoothies, yogurt, baby food, and baked goods. Dried bananas and banana chips are transported to grocery stores, convenience shops, and online retailers, where they are sold as snacks. Advanced inventory management systems track product movement in real time, ensuring that retailers receive fresh supplies while minimizing storage time. Sustainability initiatives play an increasingly vital role in banana processing. Many factories implement zero-waste policies, where byproducts such as banana peels and unused fruit are repurposed rather than discarded. Some facilities process banana peels into animal feed, organic fertilizers, or even bioplastics. Others convert banana waste into bioethanol, an alternative fuel source that reduces dependence on fossil fuels. Water conservation measures, such as recycling systems that purify and reuse water from the washing process, further contribute to the industry's environmental responsibility. Technology continues to drive innovation in banana processing, with artificial intelligence and automation enhancing efficiency and reducing operational costs. AI-driven quality control systems detect imperfections with greater precision than human inspectors, ensuring that only the best bananas make it to market. Machine learning algorithms analyze production data in real time, identifying trends that allow factories to optimize processing speeds, reduce waste, and improve overall efficiency. Robotics are increasingly integrated into packaging lines, where they handle delicate bananas with minimal risk of damage. As the demand for banana-based products grows, factories are expanding their product lines to cater to evolving consumer preferences. Beyond traditional banana puree, chips, and dried fruit, manufacturers are introducing new items such as banana flour, freeze-dried banana powder, and protein-enriched banana-based snacks. These innovations cater to health-conscious consumers seeking natural, minimally processed foods with high nutritional value. From plantation to processing facility to final distribution, banana production is a seamless operation that combines agricultural expertise, advanced manufacturing techniques, and sustainable practices. The ability to efficiently process and transport bananas on a massive scale ensures that consumers worldwide continue to enjoy this beloved fruit in various forms. Whether eaten fresh, blended into a smoothie, baked into goods, or enjoyed as a crispy snack, bananas remain one of the most versatile and widely consumed fruits globally. Once banana products are processed and packaged, they must be distributed efficiently to reach retailers, food manufacturers, and consumers worldwide. For fresh bananas, the final stage of ripening takes place in specialized ripening centers located near major markets. These centers use advanced ethylene gas chambers to trigger the banana's natural ripening process, ensuring they develop the ideal color, texture, and sweetness before being shipped to grocery stores. Temperature and humidity are carefully controlled during this stage, preventing premature spoilage while allowing for even ripening across each batch. Once the bananas reach their optimal ripeness, they are packed into ventilated boxes and loaded onto temperature-controlled trucks for final distribution. Processed banana products such as banana chips, dried bananas, and banana puree follow a slightly different logistics pathway. Since these products have a longer shelf life than fresh bananas, they are stored in climate-controlled warehouses before being shipped to retailers, wholesalers, and food manufacturers. Advanced inventory tracking systems monitor stock levels in real time, ensuring that shipments are distributed efficiently while minimizing excess inventory and storage costs. Many factories have implemented just-in-time manufacturing strategies, producing banana-based products based on real-time demand forecasts to reduce overproduction and food waste. Banana puree, in particular, is a key ingredient in a wide range of food products, including baby food, yogurts, smoothies, baked goods, and sauces. Bulk shipments of banana puree are transported in large aseptic containers or barrels, which keep the product sterile and fresh without the need for refrigeration. These containers are shipped directly to food manufacturing plants, where the puree is incorporated into various recipes. Some food companies also receive freeze-dried banana powder, which can be easily rehydrated and used in an assortment of food and beverage applications. Dried bananas and banana chips are transported in airtight packaging that preserves their crunch and prevents moisture absorption. Retailers often display these products alongside other dried fruit snacks, appealing to health-conscious consumers looking for natural, convenient snack options. The packaging of banana chips is designed to be lightweight yet durable, ensuring that the chips remain intact during shipping and storage. Many brands use nitrogen flushing to replace oxygen inside the packaging, which helps prevent oxidation and extends shelf life. One of the biggest challenges in banana production is maintaining sustainability and ethical sourcing. Given the vast scale of banana cultivation and processing, the industry has faced increasing scrutiny regarding environmental impact, labor conditions, and fair trade practices. To address these concerns, many banana processing facilities have adopted sustainable sourcing policies, ensuring that bananas are grown using environmentally friendly agricultural methods. These initiatives include reducing pesticide use, conserving water through efficient irrigation techniques, and promoting biodiversity in banana plantations. Fair trade certification has also become a key factor in the banana industry,